Okay, so in this lecture, we are going to start with matrix algebra from very basics. Okay, and as the lecture progresses, we are going to take it to a good level of understanding. We'll also couple it using some linear vector space also. However, linear algebra would be taught in a separate lecture series. But somehow, since matrices and matrices without having a the discussions of matrices without having a say of a linear vector space seems to be not justified. So I'll use some of the linear vector space here itself, and this is something that you will find extremely beneficial for your quantum mechanics part also, because once you are used to matrices, especially Hermitian matrices, then quantum mechanics becomes quite easy for you. Okay, because after all, in quantum mechanics the observables are replaced by operators, and operators are nothing but matrices in matrix formulation by Heisenberg. So when Heisenberg proposed the matrix mechanics or matrix formalism of quantum mechanics, so matrices becomes quite indispensable to understand especially quantum mechanics. Also, diagonalization as a phenomena, as a concept, is very important in physics, because you see, whenever you have to find the principal like whenever you have to diagonalize moment of inertia in order to find the principal moment of inertia, all those things are very important for your exam and otherwise also in physics. So without wasting time, let us start. But I'm going to take it a very short lecture today, and I'm going to discuss only sort of definitions, and slowly I'm going to build up in this topic. Okay, so I hope you will cooperate in this particular lecture series. So without wasting time, let us start matrix algebra. Okay, okay, okay. So someone says good morning to you. So the topic that we are going to take today is matrix algebra. Okay, matrix algebra. Okay, so first thing that comes to mind is the definition for the matrix itself. What is a matrix? What do you think a matrix should be called? And always remember, as I told, the applications are many. You can find the applications of matrices everywhere in the physics. Basically, otherwise also it actually makes your space compact. When the space becomes very compact when you discuss something. So instead of solving equations, it's better to write equations in the form of matrix, and then things will become very easy. Okay, so matrix is, so I will write an M cross N matrix is nothing but an M cross N matrix is nothing but an arrangement. It is an arrangement of Mn objects, where M is the number of rows, and Mn objects, and these Mn objects need not be necessarily need not be necessarily distinct. They may be equal as well, but in general, these Mn objects in M rows and N columns. In M rows and N columns. Okay, and we actually denote it this way: A11, A12, A13 dash dash dash, A1n, and here you have A21, A22, A23 dash dash dash, A2n, and this is AN1, AN2, AN3 dash dash dash, ANn. This is how you denote your matrix. This is how we denote our matrix. Okay. Now, in general, we say that the general element is Aij, where where Ij is simply I is simply the row number of the row, and J is actually the column. Okay, if each of these Aij's are real, then we say that this is a real matrix that we are talking about. This is the real matrix that we are talking about. And if there are complex entries, in one or more elements, if one or more elements contains a complex entry, or one of the more elements is a complex number, then we say that we are dealing with a complex matrix. Then we'll say that we are dealing with a complex matrix. Okay, so I hope it is quite clear. What is a row matrix then? Row matrix is one where you will have only row. So all these things are definitions. I'm just going to write it so that it remains in your notes also. What would be a row vector? So generally row vector or row matrix, I should not use row matrix, that would not be a right term to use. So row vector I would use. So a matrix of order 1 cross n, that is it has one row and n column. This is called as the row vector, generally denoted by this a11, a12 dash 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 a1. And if I'm talking about column vector, it is nothing but it is a matrix of order, let us say n cross 1, and it has n rows, but it has one column. I think it should be okay. It should be n rows. Okay, that would be okay. It should be n rows and one column. And generally denoted, this is how it is denoted. Let me write it. So it would be denoted by this way: a11, a12 dash dash dash. Sorry, a. Instead of a, I will use b. That would be better. b11, b2, b11, b21 dash 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 bn. Okay, or simply I can write it in this fashion: b1, b2 dash dash dash. Let us say I'm writing n. Okay. Okay, so this is also I can express. I mean, compactively I can express this way. Okay. Is there any issue? I don't think there is an issue. Okay, so this is going to be a very brief, or you can say very. I know this is a boring lecture, but somehow, because I want you people to have a compact note, so I'm writing all these things so that once I'm going to write things up like eigenvalues and eigenvectors, you don't get confused in any of these things. Okay, if in precisely in physics we would be more interested in square matrices, but if m and n are different, then we say that you can say a matrix of order, a matrix A of order m into n is called as the rectangular matrix, where m is not equal to n. Most often in physics we will be interested with the square matrices. Okay, and if m is equal to n, so let us say I'm talking about a square matrix, and if m is equal to n, okay, I'm just writing it above. So if m is equal to n, that is, let's say n cross n I'm talking about, then this matrix is called as the square matrix. This matrix is called as the square matrix. This matrix is called as a square matrix, and these elements on the diagonal side we call as the diagonal elements. Let's say these elements. So these elements would be what? This would be a11, a22, a33 dash 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 a and n. These elements are called as the diagonal elements. These elements are called as the diagonal elements. These elements are called as the diagonal elements. And if we sum these diagonal elements, the sum of these diagonal elements, that is this is at times referred to as the principal diagonal or the main diagonal. So I'll write it here. This is at times referred to as the principal diagonal or the main diagonal. Okay, so principal diagonal or main diagonal. So this is called as the principal diagonal or the main diagonal, and the elements lying over it, these are called as the diagonal elements, and some of these diagonal elements of a square matrix is referred by a special name called as the trace of the matrix. The sum of the diagonal elements of a square matrix is referred by a special name called as the trace of the matrix. I hope you're not getting bored. Kindly let me know in the comment section if you're getting bored, but actually I will have to do all these things, and once I'm done with these things, like once I'm done with giving you all the properties, then we'll do the questions. So probably from tomorrow we'll do the questions, don't worry, but today kindly cooperate today, just for the day, because see, if you're making notes for your exam, you should have each and everything written so that you don't get confused anywhere. So the sum of the diagonal elements of a square matrix is called as the trace of the matrix. Now this, if all the elements are zero, then this is called as a null matrix. So what is a null matrix? Null matrix is that matrix where all the aij's are equal to zero. All the aij's are equal to zero. And a diagonal matrix is one where all the off diagonal elements are zero, but diagonal elements exist. So what is a diagonal matrix? I'm writing what is a diagonal matrix. What is a diagonal matrix? So I'm writing a diagonal matrix here: A11, A22 dash dash dash, ANN, and all these elements will be there. All these elements will be there. All these elements will be there. And all these elements here, these are non-zero elements. Sorry, these are non-zero elements. These are zero elements. So I'll write that these elements here, the diagonal elements are there, but the off diagonal elements are zero. So all these elements I'm writing. So off diagonal elements are zero. So off diagonal elements are zero, but along the diagonal, the elements along the principal diagonal, these are non-zero. Okay. In particular, one of the matrix where all the one of the particular matrix, a diagonal matrix with all diagonal elements equal to 1, with all diagonal elements equal to 1 is referred by a special name called as the identity matrix, or sometimes unit matrix also. Identity or unit matrix. So the only diagonal elements are present. Off diagonal elements are 0. I'm so sorry for the mistake. So off diagonal elements are 0, but the diagonal elements are there. And this is called as the diagonal matrix. And in particular, diagonal matrix with all the diagonal elements equals to 1, they are called as this is in special referred to as the identity matrix or the unit matrix. Okay. Now, when do you say that matrix is equal? When do you say that your matrix is equal? I'll write it here. So two matrices A and B. Let us say I'm writing A as Aij, and let us say the matrix order is M cross N. And let us take general matrix B, which is P cross Q. The two matrices are said to be equal only if they have the same order. First thing, they should have both same order, by which I mean M should be equals to P and N should be equals to Q. And further, each of the elements are also the same. Each of the elements are also the same. That is, Aij must be equal to Bij for all ij. Only then I can say that the two matrices are equal. Two matrices are equal. When you multiply a matrix by a scalar, each of the elements get multiplied. So if I multiply, let's say my matrix is Aij, that is A is a matrix of M cross N, and each of the elements are represented by Aij. If I want to find another matrix which is alpha times A, it is nothing but it is equivalent to multiplying all the elements in the matrix by alpha. So this would be a new matrix alpha times A, B is equal to alpha times A. Further, if I want to add or subtract, so let us say I have addition or subtraction. So if I want to add a matrix, add two matrix and subtract two other matrix, but understand both should be of same order. Both must be of same order. Otherwise, it does not make sense. Both must be of same order. Both must be of same order. So if both are of the same order, let us say I'm saying A is equal to Aij and B is equal to, let us say, Bij. Then the sum C, which I can write as, let's say, Cij, would be nothing but it is equal to Aij plus Bij. Each of the elements would be added. Like A11 would be added to B11, A12 would be added to B12. And similarly, if I'm defining D, which is nothing but it is equals to A minus B, then it would be equals to Aij minus of Bij for all Ij. Okay, I hope it is clear. Now, these are just definitions that I'm giving today. I'm going to start with the questions tomorrow, but these are important definitions you should keep in mind. So if A1, A2, A3, dash dash dash, AP are, let's say, P matrices which can be added, that is, which are of the same order, or I can say which are conformable for the addition, which are conformable for addition, which are conformable for addition. And let us say alpha 1, alpha 2, dash dash dash, alpha p are p scalars. Let us say alpha 1, alpha 2, alpha 3, dash dash dash, alpha 1, alpha 2, dash dash dash, alpha p are p scalars. Then alpha 1 into A1 plus alpha 2 into A2 dash 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 alpha p, and this is matrix, by the way, this is matrix, this is being multiplied with a scalar. This is called as the linear combination of a matrix. This is a linear combination of P matrices. In fact, it will not disturb the order. Order will remain the same. The order, let us say this matrix is, let's say, C. The order of C is same as that of any of these AIs. Is same as that of any of these AIs. I hope it is clear. I don't think there is anything required to be explained here. I think all of you are quite aware of this. I'm just doing it so that you should remember all these things, and once you remember all those things, then it will be easy for us to go ahead and do matrices, eigenvalues, eigenvectors, some vector spaces, and all those things. So it will be easy for you. So I'll do in this particular session all these things so that you don't lag anywhere. I don't want you to lag anywhere. That is the main thing. Okay, so you will have to have certain amount of patience when I'm doing this. Please keep this patience, and then I'm making you sure that we're going to do a lot amount of difficult stuff as well. Okay, so we'll do a difficult stuff as well. Okay, now let us go a little bit ahead, and let us write a few more properties. So if properties of the matrix addition. So there are different properties of matrix addition that needs to be written here. I'm writing all those things. And scalar multiplication. Okay, so properties for the matrix addition, or of the matrix addition and the scalar multiplication. So if I'm writing this, a plus b is equal to b plus a. That the first thing is that the addition is commutative. Addition is commutative. Second thing that you should remember, it is associative as well. That is, if you want to write the, if you want to add a plus b and then c, or whether you add a to b plus c, this is one and the same thing. So associativity also hold. And this is very important in formulating the definition for vector space and things like that. So please understand all these things. If I add to a to a null matrix, it will remain a. If I add a to a negative of a, it will give me a null matrix. If I multiply a by alpha plus beta, then this alpha get distributed, and alpha, like this addition, gets distributed over this multiplication. And if I have this identity element, I multiply it by 1. This is 1 multiplied with a, it will give me 1, and there is 0 if I multiply it with, this is not matrix, this is not matrix, this is in general, this is in general any element 0. So this is a matrix which I'm making by bold. So I'm making it by bold. Okay, so how should I make it bold? Just give me a minute. Okay, so this is 0 element, this is I think scalar, I should write. This is just a scalar. I'm multiplying it with a, I'm getting a bold 0. This is a null matrix, and I'm multiplying with 1. This is, you can say, scalar 1. Just to show it from different color, this is scalar 1, and I'm getting a bold a. That is, I'm getting the matrix itself. So these are some of the properties regarding matrix addition and scalar multiplication. I think these are very easy things for you. Now, multiplication. Multiplication of two matrices. Okay, so multiplication of two matrices. So multiplication of two matrices. So let us say, what is the condition when two matrices can be multiplied? So let us say there is a matrix A, and let us say that this is of order some m into n, and let us say another matrix is B, which is Bij, and it is of order what? Only when you can have this multiplication. So always remember, for a multiplication to happen, number of rows, number of columns in A must be equal to number of rows in B. Only then your multiplication would be possible. So number of rows in A is what? Number of rows in A is n. Number of columns in A is what? Number of columns in A is n. And what is number of rows in B? So number of rows in B should be n. Only then your multiplication is possible. Otherwise, you cannot have a multiplication. I think this is something that you know from your standard 12th. So this is how it can be. And if I multiply these two matrices, that is, if I want to find AB, this will be I'm writing what it would be, but it would be a matrix of order. It would be a matrix. Let me write it as M cross. I have written directly this n cross p. I never wanted to write this. Just give me a minute. Okay, sorry. So what I wanted to explain you, that let A be a matrix of n cross n, m cross n, and let B be a matrix of n cross p. Let B be a matrix of n cross p. Why I was saying this? See, always remember, when I think this is quite obvious, but okay, but just telling you that number of columns in A must be equal to number of rows in B. Only then you can have this multiplication possible. Otherwise, you will not be able to have a multiplication. And this product matrix AB comes out to be order of m cross p. So the order of matrix is m cross p. The order of matrix is m cross p. So I think this is quite easy, but just for the sake of writing it, I'm writing. So this is 1C. So what would be C? C would be simplyCij's. And what would beCij's? It would be equals to AB. And how do you multiply? I think this is something that you know, but still if somebody's want to have initial understanding to all these things, let me draw it a matrix. So this will be A11, this is A12, and this dash 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 A1n, and there you have A21, A22, dash 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 A2n, A31, A32, dash 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 A3n, AN1, AN2 dash 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 ANN. Sorry, AM1, AM2, and this is AMN, right? This is M cross N, right? This was M cross N. Okay, and let us take a general case also so that you don't get confused. So let us take a general case also in between somewhere. I'll take a general case so that it will look better then. Okay, just give me a minute, I think. Okay. Okay, so let us take a general case also, then you will be able to understand. I'm writing a general case in this. So I'm writing AI1, AI2, AI3 dash 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 AIN. This is the general one. And the last one would be AM1, AM2 dash 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 AMN. Okay, so this is one. Now here this is B that I'm writing right now. Just give me a minute. Okay. Okay, just give me a minute. Okay. And now I'm writing this B matrix. And what is this B matrix? This B matrix is given by B11, B12, dash dash. Remember, this B matrix is N cross P. This B matrix is N cross P. So number of rows is M, number of columns is P. So this will last till B1P. Okay, and this will be B21, B22, dash 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 B2P. And let us write just one. So what you do, you actually take this row and multiply with the column. And what is that column? I'm writing it here. So here it is I1, I2, I3, IN. Here it would be, let's say B1J, B2J, dash dash dash. And what would be here? I think there are, how many rows are there? N rows are there. So N in J. And here you will have this thing. Bn1, Bn2, dash dash dash, Bnj, and here you have Bnp. Okay, I hope everybody is following this. I think this is quite easy to see. This is M cross N matrix, and this is N cross P matrix. Only if the number of columns in A is equals to the number of rows in B, only then your multiplication is feasible, otherwise not. Then what do you get? What is your Cij? So Cij, the general element for this is general element of this product matrix is the general element of this product matrix is okay. So general element of this product matrix is AI1 into B. What was that? I think it was N. What was that? Just give me the first element, B1J. Sorry. So the first element would be here B1J. Then plus AI2 into B2J plus AI3 into B3J dash dash plus 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 AIN into BNJ. This is how you define the general product element. So I can write that Cij can be written as summations. Just give one thing as an index. So I'm giving K as index, and here you have AIK multiplied with BKJ. So this is how you represent your general element of the matrix, product matrix. So I hope this is quite easy to identify. In general, whenever we do this, there is a terminology that we use. We use that B is being post multiplied. So I'm just writing it here. We say that B is being post multiplied. Or if we have to refer to A, we say that A is being pre-multiplied. Just to understand, A is being pre-multiplied. I hope it is clear. This is something that I know you all of you know, but just for the sake of writing, I'm writing so that you should not have incomplete notes anyway. I don't want you to have incomplete notes. That's why I'm just doing it for you. Now just try to solve a problem for me, and then we'll move ahead. I think that's not a very difficult problem. Just giving you a simple problem. just try to find the values of this. Just try to find, I'm giving you a question, just try to find this. So just try to find a square minus a plus d a plus ad minus bc times identity, what it would be equals to if a is equals to ab cd and a b c d are any scalars, real scalars. They are real scalars. So if a b c d are real scalars, I want to identify what it would be. What would be a square minus a plus d times a plus ad minus bc times identity. I'm giving you 1 minute to solve this particular problem. If you're able to solve, fine. If you're not able to solve, I'll solve it for you. Just 1 minute. It's easy thing to multiply a square matrix. It does not take time. So a square is a being multiplied to itself. So how would you do this? It's very easy to see. I think what would be a square? So I'm writing a b c d, and again I'm writing a b c d. Okay. Now you have to do this particular thing. So what you will get? I think you will get a square plus bc here. Here you will get ab plus bd. Here we get ac plus cd, and then you will get, I think, bc plus d square. I think this is quite easy to see. What would be I'm writing a plus d times a. So this is a scalar multiplication of a matrix. So each of these elements will get multiplied. So I'm writing it directly, a square plus ad, ab plus bd, ac plus cd, and ad plus d square. This is your 1, this is your 2, and then you have this identity. So what is identity? So identity is simply ad minus bc. If you multiply with identity, it will give you what? It will give you ad minus bc here, and it will also give you ad minus bc here, and all other terms will be 0. So forget about it. Now add this, add this, add this. I think this is quite easy to see. What it would be equal to? Kindly let me know. If I add all of them, what it will be equal to? If I'm not sorry, I think if the equation was a square minus a plus d times a plus ad minus bc identity. What it will be equals to? Just let me know. So a square cancel, bc and bc would cancel, ad minus ad would be cancelled. I think the first term would be 0, other term would be 0, 0, 0. I think it should be a null matrix. Just let me know. Everybody is getting a null matrix? Yes or no? Everybody is getting a null matrix? Yes or no? I don't know how many people are live. Please let me know if everybody is getting a null matrix. Okay, I guess nobody is getting it or something. Okay, fine. So this is one thing that I wanted to tell you, that you should be able to recognize all these matrices. Point number 1. Now I hope everybody is getting the matrix. Okay. Okay. I think these are all easy questions, but just for the because see any topic, if you start from very basic, so that even if some lagging is there, you'll be able to understand that particular lag and you can work over it. Because at times it may so happen that you're not in you're not that in flow, and some notes you can take. So for example, it is always possible that for a matrix A and B, AB is defined but BA is not. It may so happen that AB is defined but BA is not. Okay. So for example, if let's say if I'm taking that A matrix to be of order 2 cross 3 and B to be of 3 cross 4, then obviously product matrix AB is defined, but BA is not defined. Okay, but the matrix BA is not defined. Are you getting my point? Okay, so always remember, it is not always necessary that if AB is defined, then BA has to be defined. Okay, so this is one. Second thing, if at all, here we took the rectangular cases now. So if I take the square matrices, then it is fine. So if both product matrices AB and BA are defined, if both AB and BA are defined, then it is only possible if AB and BA are square matrices. In general, therefore you can never say that AB is equal to B. In general you cannot say that AB is equal to BA. It can be specific case where you can have AB equal to BA. So in general, the matrix product is not commutative. Okay, in general you cannot say AB is equal to BA. So always remember, matrix product in general is not commutative. Okay, then third point, uh, just uh, uh, just I'm asking you in question wise. Okay, let me ask this thing in question wise. So if AB is equal to 0, does it imply A has to be 0 and B has to be 0? Does it always imply that A has to be 0 and B has to be 0? Both have to be 0? That is, if AB is equal to 0, then is it true that both matrices A and B must be 0? Both matrices A and B must be null matrices? Both matrices A and B must be null matrices. No. Yes, good. So I think this is quite clear to you that if I just take, let's say for example, I'll just do one thing. I'll take a column 0, and what I'll do, I'll take a row 0 here. So I think you'll be able to understand it quite easily. Now you just do AB. You just do AB. What will be AB? A would be 0, 0, 0, and again 0. So AB would be a null matrix. What do you think BA would be? What do you think BA would be? Because here it is a square matrix, so here you can try this also. So what would be BA? What do you think BA would be? BA would be 0, 0, AX plus BY, and then 0. So certainly this is not equals to AB because this is not a null matrix. So again, BA in general is not equals to AB. Please remember. Okay. In general, there is a special name to a matrix which is called as the nilpotent matrix. So I'm writing nil, and we're going to study each of these matrices in detail when we are going to do eigenvalues. So please keep a few days patience, uh, because then I'll use directly nilpotent matrix and probably you'll not be able to understand what I'm saying. Okay, so for a nilpotent matrix, let us define a k product of matrix A. So A multiplied k times. This is AK. Then a matrix AK equal to 0 for some positive integer k is said to be nilpotent. So let's say if there is a k product of a matrix, if I'm doing a k product of a matrix, if I'm multiplying a matrix by itself k times, then and if AK is equals to 0, then it is said to be a nilpotent matrix. In fact, this particular k is also called as the index of nilpotency. So what should I say? The smallest value of k, because if you multiply further with a, if AK is 0, then even higher multiplication would yield you 0. But what I'm referring to the smallest value. The smallest value of k, the smallest value of k for which AK is equal to 0 is called as the index of nilpotency. Is called as the index of nilpotency of the matrix A. And in fact, one more matrix I'm going to write, and then I'm going to conclude this lecture. This is called as idempotent matrix. And when you're going to study the projection operator in quantum mechanics, you'll see that that is an idempotent that forms an idempotent matrix. So idempotent matrix. So if your matrix is such that if A square is equal to A, then this is referred to as your idempotent matrix. I hope it is very clear. A few properties that you should note about multiplication. So for properties I'm giving you, properties of matrix multiplication I'm giving you. Why I'm giving you all these things? Because I'm going to take it into vector space. Then you'll need all these things. So if there are three matrices, let's say A is of order, let me take it as m cross n. Let me take B of n cross p. Let me take C of p cross q. Then AB times C you take, or you take A times BC. They are one and the same thing. And this matrix will be of order p m cross q. This matrix will be of order m cross q. This product matrix AB times C is equal to A times BC. This will be of order m cross q. Is that fine? I hope it is fine. Just don't worry. In a few days, I'm going to start with difficult things, but just for today, keep these things in mind. If you have this A of order m cross n and B and C, let us say that these are two matrices. Let us say that B and C are two matrices. B is of order, let's say n cross p, and let me take C also of order n cross p. Then I can also define distributivity, that is A times B plus C, because now I can add, because these are of the similar order. So A times B plus C is equals to AB plus BC, and this will be of order m cross p. Is that fine? And let's say if I have this thing, I can also do this. Let's say A and B are of order m cross n, and C is a matrix. C is a matrix of order n cross p. Then C is a matrix of n cross p. Then we can also define this A plus B times C. This will be equals to AC plus BC. Okay, so here this is sometimes referred to as the left distributive law, and this is sometimes referred to as right distributive law. I don't think this is of much worry to any one of you because all these things are quite easy to see. But just I wanted to start with a little bit basic so that one, that your notes remain holistic and complete, and secondly, at times we actually tend to forget a few things from our childhood. So it's better to revisit all those things. So if let me write one more thing: scalar multiplication. If A is a matrix, let's say of order m cross n, and B is a matrix of order n cross p. If A is a matrix of order m cross n and B is a matrix of order n cross p, then one can also multiply it using a scalar, that is AB can be performed obviously because number of rows is equal to number of columns here. So number of columns in A is equal to number of rows in B. So AB can be performed. I can multiply this with alpha and I can do all sort of these things. Okay, why I'm doing all these things? I told you I'm going to use all these things where I'm going to formulate the definitions in vector spaces. A few more important things: transpose. I hope you know. I'm just revising it for you. Okay, so what you have to do while doing transpose, you just have to interchange. You have to interchange the corresponding rows and the columns. Interchange the corresponding rows and columns of a given matrix. Of, let's say, matrix A is actually doing what? Is actually transposing the matrix A, usually denoted by A transpose. So if A is any m cross n matrix, if A is m cross n matrix, then A transpose would be what? It would be n cross m matrix. Okay. However, if you want to define A into A transpose, it will also be a square matrix. And if you want to define A transpose into A, it will also be, it would be what you can say, it would also be a square matrix. Only the order would differ. So let's say if I'm taking this to be m cross n, this to be n cross m, A into A transpose will be m cross m matrix, right? It would be m cross m square matrix. So this would be a m cross m square matrix. I'm writing it here. And I think this would be n cross n square matrix. I hope it is understood. Now, a few of the results that you should remember for transpose, and then we are going to start with the sorry, special matrices tomorrow. Then we are going to start with the special matrices like orthogonal matrix, like symmetric matrix, skew-symmetric matrix. We are going to discuss all these matrices and their eigenvalues. So that is a good discussion that we are going to do tomorrow. Always remember, if I am taking transpose and again doing a transpose, it will reproduce my matrix. If I'm doing A plus B transpose, then this particular transpose gets distributed into similar, like it becomes A transpose plus B transpose, but understand A and B must be conformal. These must conform for the addition. They must be conformable for addition. And I think this is something that you know, but still, if I'm doing AB transpose, then this is equals to B transpose times A transpose, provided A, B are again conformable for the multiplication. They must be conformable for the multiplication. And I can also generalize this if to, let's say, product of P matrices, and if I take a transpose of it, it is equals to AP transpose, AP minus 1 transpose, dash dash dash, A1 transpose. So I have this much for today. I have this much for today. and then we'll meet tomorrow with a discussion on determinants, rank, eigenvalues, eigenvectors, and so on and so forth. Uh, please do keep a patience. Please do keep a patience. Please keep a patience for a few days. Like a few days, I'm going to describe more of the, you can say, definition part, and then we are going to enter the exciting world of matrices. And once we are done with matrices, we'll also try to merge it with linear vector spaces so that you make certain sense of what is linear vector space and all. Because after all, linear vector space is the language in which your quantum mechanics works. Okay, so having a firm understanding of matrices and linear algebra would certainly help your journey of understanding quantum mechanics. So I hope I hope to meet you tomorrow. Till then, take care.